It gives me great pleasure to introduce Alain, who's going to be talking about mathematics and the brain, and this is his fourth chapter. Alain, welcome on board.
Thank you, Robin. It's great to be here again. Thank you all for coming, also online. So today I'll talk about brain dynamics, what's really going on under that thick skull of yours. Whether you think, whether you sleep, you dream, or you feel, there is a lot of activity going on in the brain. And the purpose of the lecture today is to try to understand that and, with the help of mathematics, try to get a better picture of what's really going on. But before I do so, I have a confession to make. You might not have noticed, but I'm not originally from Great Britain. I grew up in Belgium. And in Belgium, we have a particular love for comic books. So today, in homage to my childhood, where I started learning and dreaming about science through comic books, I will have that as a theme going through my lecture. And with the help of Captain Science, we'll start with first part, Electric Man. Electric Man was born in 1937. That was a dark time in the world at that period. And many minorities, especially in the US, felt persecuted and fantasized about the help of superheroes. It is the same year Superman was born. And it's somewhat relevant to what we see today. But for me, the real Electric Man was not this one, but was Hans Berger. Hans Berger was born in 1873, and he started well. As a youngster, around the age 18, 19, he decided to study mathematics. But it didn't really work out for him, and instead, foolishly, he enrolled in the Prussian army. And one day, in 1893, he had a life-changing event. He fell out of his horse and was almost run down by a horse-drawn cannon coming to him. He survived the event and went back to his barrack, and he was really astonished to find there that his sister had somewhat seen what happened to him and sent him a telegram asking him if he was all right. And he thought at the time that maybe there was some kind of release of psychic energy, very much like Professor X here, relieve the psychic energy from him to his sister that triggered her to send a telegram. At the time, it wasn't completely absurd. They had no idea about telepathy or things like that. There was no basis to not look into that. And he decided then to spend the rest of his life studying that notion of psychic energy. And he started by refining technique to study the electricity going through nerves, especially in the brain. And he perfected his techniques for years and years until in 1924, he realized with the techniques that he had that he could measure regular oscillation in the brain. It is something that people didn't know and people didn't believe at the time. Most people, scientists, thought that whatever activity they knew about electricity, nerves, and all that, but whatever activity took place in the brain was more or less chaotic. His colleagues completely ignored him. However, in this country, somebody else also thought that a little bizarre and tried to disprove it completely. And that's the very famous physiologist, Edgar Adrian, who would go to win the Nobel Prize in 1932 for his work with Sherrington on the neurons and defining the notion of synapse, as we're going to see. Edgar Adrian started redoing and perfecting the experiment. And to his surprise, he observed the same phenomena. And by the 1930s, these techniques that Hans Berger called electroencephalogram became accepted, that there was some regular pattern in the brain, some wave. So what it is, these are not routine things that you do in the hospital or for research. You put some kind of set over your head, a little helmet, with very little tiny electrode that measure the electric activity taking place at the surface of your brain, inside your brain. And what you can record are different type of waves depending on your activity. That was first observed by Berger. There are level of alertedness, meditation, deeply relaxed sleep, and that's measured in frequencies. So frequencies, the number of oscillations per unit time. So 3 hertz, you have 3 oscillations within 1 second, is typical of very, very low, deeply relaxed state, whereas 10, 12 hertz is the normal resting state, meditative states that you have, the so-called alpha waves. When you are alert and you pay attention, then you are in the beta regime that goes to 12 to 30 hertz. And there are also gamma waves that are above that. So I hope that you are either very meditative and very relaxed on the alpha place, or maybe a few of you are in the beta regime. But if you see your neighbors being in theta and delta, just don't wake them up. I hope they have a good time there. So why is that important? Because it is a crucial biomarker for brain activity. Here are an example of electroencephalogram. You see different recording at different places of the brain. And what you notice right away, as this takes place in time, a little piece of paper takes place in time, you see a huge change in activity. And that's a huge synchronization taking place within the brain right at this time. And what happened to this person is a bout of epilepsy taking place in the brain. Sudden, huge synchronization of activity within the brain that you can spot through electroencephalogram. So our purpose today is going to try to understand the origin of these brain waves. How come interaction between cells gives rise naturally to regular rhythm? There is a pattern there, and mathematics, of course, is all about understanding patterns. And from there, we can try to understand a little bit more about how the brain works and organizes itself. In order to do so, I'll have to go step by step, different scale. We're going to start at what's called the microscale, the most elementary one, which is at the cell level. Then we're going to try to understand what's going on in a little region of tissue, once you understand something at the neuron, and then at the entire brain level. So we'll start at the cell level, and we try to understand spikes. So you may remember that a neuron is really the fundamental unit of the nervous system. It's responsible for transmitting information through electrical and chemical signal. A typical neuron has 3 different parts. You can see on the left the dendrite that takes signal from other neurons in the form of neurotransmitter. So they're very close to each other and transmit this information. You have the cell body, or soma, that integrates this information. And then you have a very long branch. They can be extremely long, by meter long or tens of meter long, if it's in a blue whale. The axon that transmit information all the way to the terminal branches that will get information to another neuron, passing this information. So the neuron receives inputs from other neurons or from something else, and then transmit this information to the end of the axon and transmit the information to typically other neurons. How does that process of passing this information works? Well, the information is in the form of electricity, but not exactly the same type of electricity that happens when you turn on a switch. In order to understand that, you'll have to look at the membrane of the axon. And if you put a voltmeter, you realize that there is a difference in potential between what's inside the axon and what's outside the axon. There is a jump of potential in the membrane. So just like a very tiny battery, a battery is like 3 volts or something like that, this is 70 millivolt. We call it minus 70 millivolt by standard. So there is a tiny difference of potential between inside and outside that's due to a difference in concentration of ion, typically sodium and potassium ion, between the inside and the outside. There's a difference in charges. Okay? But what can happen also within this membrane is that you have channels. You have channels that can open or close depending on the voltage they receive, because the voltage they measure. and let ions go in or out, and changing the difference in potential between outside and inside. And it's this difference of potential, called in neuroscience action potential, that is carried through the axon and is the basic signal that we have in neurons. So the understanding of this process really came from the work of Alan Hodgkin and Henry Oxley in the 1950s. They look at the squid. The squid has a giant axon that's related to its propulsion, the way they squirt water. Particularly good to do experiment because it's very thick. It's 1 millimeter in diameter. And what they did, they were physiologists, what they did was to try to understand the mechanism from a physical perspective. And they were able not only to record the action potential as it took place, but also explain all the details of how it's actually created and transmitted. And this is one of the observations that they made. When they record that difference in potential, just like a voltmeter between the two, right? It's about the same. They realize that if you look at one place, you have a spike, and then it goes back. Right? The spike, the lower part is at minus 70 millivolt. It goes up to plus 40 millivolt or something like that. You say that in the rest state, the axon is polarized, and it depolarizes when it goes up because of the change in ions, and it repolarizes when it goes down. But they went much further. Physiology is a science that's a little bit different than your traditional science in life science, medicine and all that. It's very grounded into physical process. And what they did was not only to measure, understand the mechanism, they also created a mathematical model for the whole thing based on analogy with electrical system. And this is the Hodgkin-Huxley model, which is a set of 4 differential equations that fully describe this process. They were able to characterize all the parameters that enter the system. I'm not going to go into detail of this particular differential equation. I'll show you in more detail another one. But with that, they were able to explain everything. And it's for that perfect theory, in a way, that they won the Nobel Prize in 1963. Now, it is a fairly simple equation. Now, on a computer, you can easily simulate them. So what are the results? If I just took the equation for Hodgkin-Huxley with the parameter that they give, and I look for different type of input, what would be the output that the model gives? So the idea is to look at one place, like you would clamp it and measure the potential, and look for different values of increasing the input signal. So for a small stimulus coming in, for a small stimulus, nothing happens. So if you just kick it a little bit, it doesn't react. It doesn't pass in information. And that's very important because you don't want axon or neurons to always transmit as soon as you have a little bit of noise, right? You have to wait for the stimulus to be large enough. For medium stimulus, past a certain threshold, you have a burst of activity, the signal passes through and is transmitted at the other end to the next neuron, right? And this is what's the output of the model that just simulate on my computer, and you can compare that to the original recording that Hodgkin and Huxley obtained and see that it has all the same feature. You have a repolarization. In that time, typically a neuron is not able to receive a signal. And that ensures that this signal is very well defined in space and time, and you can think of it as one bit of information. You pass one bit, you send one spike, and you give a 1 or 0 if there is no information. So that's the core of the information that neurons are able to exchange with each other. We'll get back to information at the end of the talk, but it's just to understand that that's what neurons are able to do in a very reliable way. By having this threshold, stop the noise from coming, and by having the fact that it takes a while to repolarize, it doesn't create too much activity. However, if the stimulus is much larger, you have a different type of dynamics in this case, you have a train of spike coming in the system. So the three types of behavior can be observed, is a no behavior for small input, train of spike for larger input. The typical one is just the one spike traveling. And the typical velocity for this type of wave is about 1 to 120 meters per second. It's quite a big range, but there's a lot of huge diversity in neurons, and depending on the diameter, depending on constituent, whether they have a sheath of myelin that surround them. The sheath of myelin is mostly related to fat. So that's why you have white matter in the brain, because you have this myelin within the brain. The white matter looks like fat because it's mostly fat. And that's why it's important to give fat to babies, because they have to build this myelin sheath to have faster thought process. So huge difference in number, 1 to 100 meters per second. That feels very fast, right? 100 meters per second. But speed of sound is 300 meters per second. So that's 1/3 of the speed of sound. If I clap my hand, you might just see a little bit of difference between that. So 100 meters per second is actually not that fast. You compare to electricity, you flip the switch, the light turns out to about 1/3 of the light speed, which is 10 to the 8 meters per second. So we're talking about a difference of 1 million between electricity and action potential traveling to an axon. And why is that? Because the action potential, in order to travel, has to open this channel, and ions have to go up and down. So you're actually talking about real motion of ions and not just electricity going through, right? So it's very different. It's more, you can think of an electrochemical wave propagating. And this number, 100 meters per second, we'll see at the end, has some importance about information and information rate. Okay. Now we understand a little bit about the element, the atom of the brain, the neuron, able to do one spike. But one spike doesn't make these wave activities. We're not there yet. So how do we get waves? People remember New Wave was a comic book from 1986 to 1987. Not a big success. But the robot was called Megabyte, which I like. So next step, let's try to understand waves. And now, instead of looking at a single neuron, I will try to look at a little piece of tissue within the brain. So I want to start connecting neurons, right? I want the input of one to be the output of the other one and bring them like I would do like an electrical circuit. But of course, we don't have just 2 neurons. There are lots of neurons. And in a little region of the brain, you have a lot of neurons, and they all will start sending signal left and right. So naively, you could say, well, we can have one equation for each neuron and connect them all, but that doesn't really work. People have tried that, and it's not the best idea to try to understand the mechanism. More interesting is to look at population of neurons. And when you look at population of neurons, you find that there are 2 kinds of population of neurons. There are the excitatory neurons and the inhibitory neurons. So what's the difference? Well, imagine that excitatory neurons not only propagate information, but they also have the ability to lower the threshold of the people they're talking to. Think of it like a crowd of kids or teenagers with a few teachers. Right? Teenagers are rowdy and they start shouting, and that they lower the inhibition of the neighbors, and the neighbors start shouting also. And you have a few teachers trying to calm them down because they came here to a Gresham lecture and they have to be formal and polite. Right? So the ratio is about the same, but 10 to 20% are inhibitory neurons, who tries to dampen the activity of other neurons, right, by increasing the threshold, and 80 to 90% of the other neurons are the ones that want to really activate. So the effect of the excitatory neuron is to excite themselves, but they also have the effect of exciting the inhibitory neurons. But the effect of the inhibitory neurons is to increase the threshold, makes it harder for everybody to be activated, including themselves. Teacher always say to the other teacher, don't scream so much, quiet down. And they lower the activity of the entire population. And now the idea of the Wilson-Cohen model from 1972 is that if you couple these two, you can now look at input coming into the system, trying to knock them, and see what activity is generated by that. So it's a model, it's a mathematical model. Usually there are three different ways that a mathematical model should be explained. First, in words, like I tried. Second, in picture, like I show you. And third, of course, in mathematics, to have a completely rigorous description of what's going on. Because these interactions are not easy, so I don't know a priori what would come out of this system. Okay, this is now a system of two, very simple in a way, two ordinary differential equations, and for the activity E and I. So E is just a measure of activity, just like you would measure with electrode and something like that. How big is your signal? And so is I. What you see on the left side of the equation is d by dt, which just means the change of the activity as a function of time. It's the derivative, is the change of activity. Since we're talking about dynamics in the brain, we think we are talking about things that change in time. And things that change in time are characterized by differential equation. So the change in time of the activity of E, that's what you have on the side, is due to a number of factors. First, you have a leakage, a normal leakage that you find in all systems, that naturally the activity would go down unless something else happened. And so that's the first term, the minus E and minus I. It characterizes just an exponential decay. Then you have the excitation here that characterized by these two parameters, the weight of the connection, how strong is the effect on the other population and on itself. That's what is a plus. All the parameters here are positive. And then you have the minus here, which is the inhibition. And the inhibition is as a minus, so it lowers the change of each one. And then you have PE and PI, which is just the input, how much I kick the system, my two systems. Okay? There is one more ingredient that's very important in the system, which is the function S that you see here, is the sigmoid response. And the sigmoid response is something that's the type of response you have in all neuron systems. It tells you, just like we saw in Hodgkin-Huxley, that if the signal is too low, you won't have any change. So it's to encode that threshold. If the signal is a little higher, it's going to be proportional to the signal I receive. And if it's much higher, nothing's going to happen. It's going to saturate. You reach a certain plateau, right? So the way things change are not just proportional to how much you kick it. It's saturated at a certain level. You can only push so much your neighbor to make him do something. Okay, this sigmoid is actually very important. I call it a sigmoid for the general frame, but it is the inspiration that came from neuroscience, the understanding at that time in the 70s and the 80s, that gave the idea to people like Hopfield to start the first neural network, his paper in 1982, or Hinton, Geoffrey Hinton, in 1983, where he first described the algorithm for backpropagation. And it is at the heart of all the machine learning, artificial intelligence that we have. Not so much the sigmoid, no, there are other activation functions, but the idea that you have a nonlinear response between different elements is really what powers all that scientific revolution that we are seeing now. And that's also the reason why Hopfield and Hinton won the Nobel Prize in 2024. It is that basic understanding coming from neuroscience that was translated into algorithm. They took that inspiration for the algorithm. Okay, let's go back to our model. So we have these two equations, and we can now study, and it shows a lot of very different interesting behavior. You can have a steady state, you have a spike, but there is a regime in parameter where you can show, which is not obvious, which you just look at the system and arrows, that the evolution of both fields will actually be periodic. You naturally, because of this interaction between these two components, this coupling of multiple interaction, you have an emergent behavior that's a periodic behavior, and that underlines this basic brain waves, the alpha wave, beta wave, and all that. This is one of the ways we can understand this basic interaction. Okay, but that's still just one part of the brain. And now we want to go a little bit higher. We want to go at the entire brain, thanks to Brain Boy, who was also a telepath, but with very short-lived, with only 6 issues. So let's go at the next level. Now we've explained why you can have this oscillation in a little part of the brain. Now, in the previous lecture, we saw that we can see the brain as a set of different regions that are connected by long connection. And what you can do now is to say that each of these regions has a population of excitatory and inhibitory neurons. And the input they receive are input from other parts of the brain. So in this set, the input now is coming from other nodes of the brain. It's mostly excitatory because there is not so many inhibitory input at long distance. Inhibition is mostly at short distance. And the output also goes to other parts of the brain. And now you can think of that as all these different little units oscillating and all coupled to each other, affecting the oscillation. Mathematically, you can see 2 differential equations at each part for each node. I have here 1,000 nodes. That's 2,000 differential equations. Very easy to simulate these days. And now you can start and kick the system at one part of the brain. In the right range of the parameter, you can see what happens. In particular, you can do that, and you can model epilepsy propagation like that from one part of the brain radiating to other part of the brain. So you don't have necessarily all the brain going up and down. Seizure starts very localized and can expand around, as you see in this electroencephalogram. And the Wilson-Cohen model, or more generally what is called neuronal mass model on a network, can explain this type of activity. There is another dynamics that's quite interesting, and for that I'll have the help of Superman. I really like this picture because, as you can see, Superman has a headache. Even Superman gets headache. But this one is particularly interesting because he has a headache in the back and a headache in the front. He has 2 hits, right? And that's typical not of headache, but of migraine aura. So what is migraine aura? Migraine aura is a type of migraine that typically starts with some alteration of the visual of the vision. Like you go in a zoo and you saw an animal, and all of a sudden you see these black patterns emerging, or you see spots appearing. So there is something happening in your visual cortex, in the back of the brain, and typically, it might be due to a mechanical shock, it might be to a chemical problem, it might be due to ischemia. But what you have essentially is an imbalance in these ions, mostly potassium ions that are overfilling the extracellular space. And the effect of that is it depolarizes the neurons. They are unable to fire. And that can lead to various forms of ischemia, reduced blood, and all that. But the fact that they overcome that locally, this potential threshold, disable the neurons to be able to repolarize, to be in the normal state. Not only that, it also propagates to the neighbors. And so you have a very slow chemical wave now, diffusion wave, going from the back of the brain, slowly evolving within 10 to 15, 20 minutes to the front of the brain and giving the typical strong headache associated with migraine aura. And these are called cortical spreading depression because they spread only on the cortex and invade the whole brain like that. So these are wave. It's another type of dynamics because these are mostly chemical waves that are much, much slower. We're talking about 2 to 5 millimeters per minute. Right? So we talk about electroencephalogram. It turns out that electroencephalogram has great temporal resolution. You have a lot of points, a lot of data because you can measure current, and we're very good at that. but it has poor spatial resolution. You can only measure things that are really at the top layer of the brain. So it's restricted to that. However, there is another method that can be used to capture the brain activity at other places in the brain. It doesn't have the same temporal resolution, but it has much better spatial resolution. And that's related to the BOLD signal. And BOLD stands for blood oxygen level dependent signal. And the idea is the following, is when a region of the brain becomes active, neurons consume oxygen. You need a lot of oxygen energy in order to power the brain to see all this process to carry out all this process that we talk about. This increased metabolic demand triggers a vascular response that increases oxygen delivery with oxygen-rich blood. And so you change the ratio of deoxygenated to oxygenated blood at different parts of the brain. And oxygenated versus deoxygenated blood have different magnetic response. And so you're able to capture that in magnetic resonance imaging. So, for instance, you can put somebody in a scanner and you can ask, open your eyes or close your eyes, and at the same time, you measure the response in the back of the brain at the visual system. And what you'll see is that you're able to see the difference in the BOLD signal, how much oxygenated blood there is versus deoxygenated blood. So it really tells you about the activity, assuming that activity triggers that blood demand. And you have peak when the eyes are open, and it goes down when the eyes are closed. And if you look at the difference between the two at every part of the brain, you can isolate the activity, the part of the brain that's responsible for a given activity. And that's the basis of functional MRI that really relates now real brain activity at different places in the brain. So for instance, here's a recording of BOLD signal at two places in the brain at the top that are related to the motor cortex. And what's very interesting with this recording is that they're very close to each other, right? Despite the fact that it's at two different parts of the brain. So they show very high correlation. So how do we actually measure this correlation? Well, you can look at the time series that you have. So the red curve, let's say it's 300 seconds. So imagine that you have one value on the graph for each second. So you have a list of 300 numbers. You can do the same for the right motor cortex, another 300, X and Y. And out of that, you can measure the correlation. So we talk about the correlation in the first talk. But essentially, it gives you a number between -1 and 1, where if the signal were perfectly correlated, you would have 1, and if there is no correlation between the two, you'd have 0. So it tells you how two different parts of the brain are active or synchronized at the same time. Here you would have very high correlation. So now what's the idea? The idea is that you can map the brain in different regions, called region of interest. This is more than a century old. This is a Brodmann map. And there is a number of regions. Let's take two different regions, number 10 and 20, for instance. And you measure the activity at these 2 points. And in this case, the activity of node 10 and 20 might be very similar. You compute the correlation that gives you a number, and you do that for every single pair of regions in the brain. You measure the correlation between any two regions, and so you compute that sum. It's very straightforward to compute once you have the series. And out of that, you get a matrix where, in this case, node 10 and 20, where you put the value in that matrix that would correspond to the correlation. So that matrix now is a snapshot of how different parts of the brains are connected to each other during different tasks. The typical task in a scanner is what's called resting state. That means we put somebody in a scanner and ask them not to do anything, just rest there. And you look at the map trying to obtain these functional MRI that lead to the functional connectome. And the functional connectome is now between these two. I can map that on a brain, and put an edge between different parts of the brain depending on whether or not they're connected. The important aspect of it, which is different than the structural connectome that we saw in the last lecture, the structural connectome really records the axon going from different places in the brain, whether or not you actually have a real physical connection. Now, these connections really encode how much different parts of the brain talks to each other independently or they are physically related. There's correlation between the two, but this one is interesting because it changed in time, it changed during learning, it changed during disease, different parts of the brain operate differently, and so on. So, what do we learn from it? Now we can go one step higher, we can look at these as networks again, but now we have this functional connectome, which is a network of activity, and we can look at all the regions that are very close to each other in terms of activity. So all the nodes that are always active at the same time, if you want. And you can organize that in different communities, and you can do that systematically. There are some that are obvious. For instance, the blue one, again, is the visual cortex. There is a big region there that whenever there is a visual demand or visual processing is active. So all these regions are connected and active at the same time. There is the motor cortex at the time that's very well known. But when you look at these, just extract the mathematics of that, look at the network, and look at the nodes in these networks that are closely connected, you find different type of network within the brain. And one of these, one big important discovery, was the discovery of the default mode network that's about 20 years old, a little bit more. And this network is called the default mode network because that's the first one that people observe in resting state. It is the one that's active when you're not active. So it's very high bold activity during quiet restfulness, resting state, and much more than during any active cognition process. And so as soon as you have activity, the default mode network activity decreases and the rest of the brain increases. It's kind of the same role as the inhibitory neuron. It controls the normal activity of the brain, suppressed when nothing is going on. And for instance, you can ask, how does that change when different levels of alertness are altered? For instance, I had a coffee before I came here today. And you can ask, what is the effect of the default mode network of coffee on the default mode network? And in his recent paper 2 years ago, they show very convincingly that the connectivity within the default mode network decreases when you take coffee, or actually caffeine has the same effect. So that means your ability to ignore the world decreases, which is, of course, a well-known effect of coffee. Now, there is another network that's been identified, and that's very recent, it's from a month ago about. It's the action mode network that operates exactly when the default mode network does not operate. So it has the opposite effect than the default mode network. It's anti-correlated, meaning when one is active, the other one is passive. As soon as the default mode network becomes active, the action mode network decreases. So it's associated with any kind of goal-directed task, right? Arousal, attention, focus, action plan, and all that. This is when the action mode network becomes active and the default mode network becomes less active. And you can see that balance between able to be at rest or be alert is important in everything we do, but also in diseases. And for instance, though, there is understanding about the change of this network during depression. It's actually very subtle and very hard because depression is such a complex disease. But very recently, people have done systematic study going back to adolescence, tracking adolescence, and seeing how this network change, and have observed that people who are prone to depression actually have different type of network. That means more nodes are being enrolled in certain network than other one. And so now we have finally we're getting close to the ability to pinpoint the change that happens in the brain very early on in adolescence that are related later in life to depression. And there are also ways to try to treat that. There are different treatments that are associated with stimulating the brain. So that gives us a general idea how to connect these dynamics to generating networks and how we can study these networks and how they change during learning, disease, and so on. There's one last part that I want to talk about, is about thinking and how fast do you think you think. You have to think about that one, of course. So we'll have the help of Captain Freedom for that last part. So I want to talk about information rate. How fast do we process information within the brain? And this is based on a very recent paper that I found particularly interesting that's called The Unbearable Slowness of Being. Why do we live in such a slow world? And I try to explain it. First, let's talk about information. So information theory goes back to Claude Shannon early in the 50s that developed a theory, a mathematical theory, to try to understand information. And of course, it underlines all the digital age, everything is done. So the atom of information, the element, is the bit. And one bit is very simple, binary, is 0, 1. So with one bit of information, you can encode two things, right or wrong, white, black, left or right, and so on. There are only two choices you can make, right? That's the only thing you can encode. Now, if you have 2 bits of information, you can encode 4 different things. You can say north, east, south, west, and 0, 0 would be north, 0, 1 would be east, 1, 0, west, and so on. So with 2 bits of information, you can encode 4 things. You have a dictionary with 4 words. And you can go on, and with n bits of information, you start with 0, 0, 0 all the way to 1, 1, 1, you'll have 2 to the n possibilities, right? For instance, 20 bits gives 2 to the 20, so you can encode about 1 million words with that. Why do I choose 20 bits? Because that's related to a very well-known game, which is 20 questions. So remember the game, you have 20 questions, I just answer yes or no. So each question, I give you 1 bit of information, and you have to discover the word that I'm thinking about. Very popular, like you see in the 1950s, on American television, where everybody was very white and very male, of course. So 1 million words, and I'm going to give you a trick that always works. Right? I'm going to give you a solution, a mathematical solution to always win. All you need is a dictionary. So we know it's 1 million words, so I will encode the first word in the dictionary as 0, 0, 0, and the last one as 1, 1, 1, and so on. Turns out that in the English language, there is not 1 million words. According to the Oxford English Dictionary, there are about 600,000. You can't actually find the exact information how many words there are. Because they change all the time, they add words and so on. But 600. We really use at most 147. Most of them are archaic words. So. But let's just do it with all the words that we have. And we need 20 because 19 is not enough, right? So the first word is A, of course. First word in the dictionary. And the last word is Sisypha. Beautiful word, right? And if you ask, Sisypha is a type of weevil found in South America. Okay, so we've learned something at least today. So you think of a word, and my first question to you is the word between A and lucid, which is more or less a half of the dictionary? And you say no, then I know it's between lucid and Sisypha. Then I will ask whether it's between lucid and rock and roll. And I divide the interval like that, and then you say, yes, it is, and then I'm going to divide between lucid and rock and roll, and I'm going to go like that every time. And since I have 20 questions, I know I can always pinpoint to the right element. And that's the idea between the algorithm called binary search, which is one of the fastest algorithms to search our order list in the computer. So very important for a lot of computer processes. So that's information, 20 bits, entire dictionary. That's what you have to keep in mind. Now, think of a word. How long did it take you to come up with a word? Let's say a couple seconds. So what is the information rate? The information per unit time, where it's 20 bits, took you 2 seconds. That's about 10 bits per second. Okay, it is a rough estimate, but let's see how it carries on. Let's think about other type of process to transmit our information, for instance. One of these is typewriting. Now, a fast typist can type 120 words per minute. I do about 12 words per minute, and my kids always make fun of me. So 120 words per minute is 2 words per second. So on average, it's 5 characters per word. But you're going to tell me, yes, but wait a second, a character is not a bit, right? Because a character, there are 26 characters. That's much more information than a single bit. And you'd be wrong. Because if you ask a typist to type a random word, that value is much lower. They go much slower. And the reason is English language has a lot of structure, what we call statistics. And for instance, we type a Q, you'd have a good idea that the next letter is a U. T, often followed by H, and so on. And this type of statistic structure is not only between letters, it's the entire world. That's why typists can go fast, because they can jump on words with minimal information. So it turns out that the entropy of English is actually 1 bit per character. You don't need more than 1 bit to look at that. And that was already established, again, by Claude Shannon in the 1950s. So 1 bit per character, so let's compute that together. 2 words per second, 5 characters per word, 1 bit per character, 10 bits per second. That's how much information flows from your hands to the paper or the computer screen, right? If you're a fast typist. And unless you're Superman, of course, and you can go much faster. So 10 bits per second. What about narration? I'm not very fast at that, but turns out that the recommended narration rate is 160 words per minute. That's for normal comprehension. So same computation, 13 bits per second. Not so dissimilar, right? How about reading? These are 1,000 comic books you must read. So reading is actually very efficient, even though the speed of reading is very different. There are different types of reading. It's an entire beautiful topic on itself. But a typical reading speed for efficient learning is 120 to 150 words per minute. You can go up to 300 words per minute without losing comprehension. Fast reader, 300 words per minute. And speed reader, super speed reader, 600 words per minute. Often you see that people say that they can read much faster, like turning a book like that and memorizing it. That's nonsense. Tests have actually shown that 600 is really kind of the upper limit before you actually lose all understanding of what you read. People have that delusion that they think they know what they read. So reading very efficient. We're talking 10 to 50 bits per second. It's one of the best ways to carry information. That's where you have to read to your kids, and that's where you have to encourage them to read. How about memory? How long does it take to memorize? Here is Memory Man and Memory League. Memory League is not a league of superheroes, as you would guess. Memory League is actually a society that organizes contests for people who like to memorize things and compete on that ground. One of them is very interesting. It's called the 5-minute binary test. And you're given a sheet of paper, like this one, where each one has 30 binary characters, 1 is 0 randomly, and you asked to memorize as many as you can. And then you are asked to recall that information, right? Maybe we should try, but again, I'd be very terrible. I think I managed the 3 first one. But the world record is 1,467 digits, 50 lines like that in 5 minutes memorize. Right, amazing, right? Amazing, but look at the information rate, the time it takes to put that information into your brain. you have 1,467 digits in 30 seconds. That's 5 bits per second, right? So if you spend your life doing that, your awakened life, you would only store 1 to 2 gigabytes over a lifetime, which is what you can get into this storage device. So for the young people in the audience, this is an archaic storage device that your parents used to carry files from one computer to another one. Completely crazy, I know. So 1 or 2 gigabytes is over a lifetime. Other estimate about the maximal amount that you can memorize based just on the brain physiology or brain architecture, just counting the synapse, is 5 terabytes, but that's way overestimating. So you're somewhere in between. Over your lifetime, you're much more likely to be in the gigabyte range. What about speed cubing? Another amazing feat of people doing something very quickly, right, in terms of cognition. So you're given 5.5 seconds for inspection, see, and you have to make up a plan about what you're going to do. It turns out the Rubik's Cube, of course, is very difficult, and there are 2 to the 65 possibilities. But that's only 65 digits, right? So information rate, 65 digits, 5.5 seconds, that's about 12 bits per second. Unless, of course, you like the Hulk and you find other ways to solve the cube much faster. So here we have an interesting problem, and that's why I call the slowness paradox, is that let's be optimistic, and maybe my estimate were a little bit on the not so optimistic side, and let's see 100 or even 1,000 bits per second. Let's just say 100 bits per second to be optimistic. That's quite slow compared to what we have around us. Again, this one thumb drive use is USB, and the transfer rate of the 3.1 standard is 10 gigabits per second. So 10 gigabits is 10 to the 10 bits per second. So that's the rate of information when I plug that in my computer is 100 million times faster than our brain process information, right? So that's interesting. But that's not really the paradox yet. That's just the difference between electric system or digital system and wet system or brain system. The paradox is the following, is that the sensory information that we get comes at a much, much higher rate. Take the eye, for instance. An eye cone within the retina, eye cone receptor, it's been measured, can get information about 270 bits per second, right? That doesn't seem too much, but there are 6 million cones in one eye. And so the information that's produced by the eye, sent initially to the brain, is 1.6 gigabit per second, right? So that's a lot of very fast information coming in the brain. This is, as soon as it quits the retina, it's being carried by the neurons. It's actually reduced. There are about 2 bits per spike at 50 hertz. That's what we saw initially. It's reduced very dramatically from 1.6 gigabyte to 100 megabit per second. So what is the slowness paradox? Well, the information comes as a gigabit level per second, and we process information at 5 to 100 bits per second, right? So there is a slowing down, a compression factor between what's the input coming in and how slowly we process information, right? And that compression factor, gigabit by 10, is 1 million to 100 million, let's say. Huge compression factor. So that's one of the biggest numbers that's not understood about information within the brain. That's why I call it a paradox, and that's why I don't have an answer for you. But I see a lot of brilliant minds, and they can put their mind, their slow and fast mind, in order to solve it. What is clear is that we don't have an electronic brain, like the man with the electronic brain, that would be much, much faster, right? We live in a world that's designed for the 10 bits per second. You get to an intersection with your car, the light comes in, you have time to do this and that, the information comes in, and you process that information. Compare that to an automated robotic plant where things zip, 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 zip everywhere, right? With a completely different rate of information propagation. We live in a slow life compared to other processes. I'm going to leave you with that thought, but I'm going to finish with one of the slowest, but also the cruelest process that's taking place in the brain. We saw things at the level of milliseconds, seconds, hours, days, learning, and all that. But there is one that takes place within the brain, originally in a certain part of the brain, where toxic proteins start to accumulate, and very slowly, over the time of 10, 20 years, propagate to the entire brain, damage the brain, and makes it completely inefficient, and leads eventually to dementia. And in the next lecture, we will study this very somber, very serious problem and see how mathematics can help us understand the mechanism underlying dementia and how also it takes place within the brain. What is the patterns, spatiotemporal evolution of this disease within the brain? And that's it for today. Thank you.